All right, let's get going. Today we're going to start talking about doing linear regression models with the rstanarm R package, which if you don't have it already, you need to install from CRAN. It's just a regular installation. So this sort of addresses what you might think is kind of a weird state of affairs with applying quantitative methods, particularly if you look under the surface a little bit. Almost everybody today that's doing quantitative methods accepts the Bayesian conception of probability, that it's a degree of belief in things that you don't know. So asking questions like, what's the probability that this parameter or whatever is positive given the data that I have? So that is a very Bayesian question. It doesn't even seem like a Bayesian question. It just seems like the sort of question that you would want to ask if you were doing quantitative methods. However, that's a question that is illegal under the frequentist view of probability, where the probability of something is the proportion of times that it happens, and the limit as the number of trials goes to infinity. So to ask, or to try to ask the question, what is the probability that this parameter is positive, is to say, what is the proportion of times that this parameter is positive? And that doesn't make sense because the parameter is not a random variable. It's either positive all the time or never positive. The only thing that you can make probability statements about are random variables, which from the frequentist perspective is the estimator. So you can ask, what is the proportion of times we point estimate the parameter to be positive, conditional on the parameters, as we do it over and over, and the limit as the number of data sets collected goes to infinity. Now, no one actually asked that frequentist question. But in any sort of real world setting, I think outside of homework problems, I've been asked one frequentist question ever. And I get asked a lot of weird stuff, but only one sort of genuinely frequentist question. Somebody wanted to know the distribution of an estimator over different random samples of the primary sampling units. Now, it's not clear that they really knew what they were talking about. It is clear that it was the biggest disaster that I've ever been involved in from a money perspective. But it was the only time that I was asked a frequentist question. All the other questions that you ever encountered in sort of the day-to-day, Starbucks or whatever, are Bayesian questions about expressing your uncertainty about unknown quantities that you might have a hypothesis about, or you might need to make a decision that is, affected by whatever is the unknown state of the parameters in the model that you're thinking about. So almost everyone today accepts the Bayesian conception of probability. Now, that wasn't true 100 years ago, when the sort of frequentist view of probability was very influential for Fisher, and everywhere that Fisher had an important influence on. It's not super clear how prevalent that was among people who were actually estimating things, but among methodologists 100 years ago, there was actually much more of a debate as to what is the appropriate conception of probability. But almost everyone is Bayesian in the sense of the definition of probability today. However, if you look at what people are doing in published articles in journals, if you look what people are doing when they work in industry or whatever, almost all the people only use estimators, deterministic estimators that have only a frequentist justification. Yes?
I feel like a really loud metallic feedback.
Yes.
Okay, I am. Is there a way to...
Apparently it's been going on all afternoon.
Oh, it's nuts. All right.
So, yeah, I've turned the volume off on this thing, but... Anyway. So if you look at journals and whatnot, what you see almost all people doing all of the time is using estimators that only have a frequentist justification. And if you sort of combine the Bayesian conception of probability with estimators that have a frequentist justification, you get people making horrific mistakes, like interpreting a p-value as the probability that the null hypothesis is true, or interpreting a 95% confidence interval as having 95% chance that it's going to include the true parameter, or, you know, I don't really know what standard errors are, but I did comma robust, and it's sort of like a vague, you know, sense of uncertainty. Things that are wrong from the frequentist perspective and the Bayesian perspective. So there is no one who agrees that any of those statements make any sense at all. But you see journals just filled with them. And, you know, as a result, a couple of years ago, the Journal of the American Statistical Association assembled their like council of 27 wise guys or whatever to come up with recommendations as to what to do, you know, for journals as to how they should treat p-values. And they couldn't really completely agree on anything because 27 people can never agree on all things. But the one thing they did sort of agree on was to make it the policy of the American Statistical Association that p-values should not be used to decide what papers get published or really for anything else in terms of like making a decision about them. So they put out a special issue of the Journal of the American Statistical Association journal, and everybody, you know, wrote some stuff, and they, you know, said why they came to this recommendation. And for the most part, in sort of frequentist land, nothing changed. They kept on, you know, journals still published p-values for the most part, and just sort of carried on the way that they'd done for decades previously. Now, political analysis adopted a policy of banning p-values. Some other, you know, journals have done similar things. I don't think that was so much as a result of the American Statistical Association saying that p-values shouldn't be used for anything, so much as the political analysis, which is the sort of methodology journal in political science, finally got an actual Bayesian to be editor of it, and he just said we're not doing any p-values anymore. But anyway, so not a whole lot changed from the perspective of, you know, what a lot of people have been doing for the last, you know, long amount of time. So we're in this weird situation where almost everybody accepts the Bayesian conception of probability. Almost none of those people are using Bayesian estimators. They're using frequentist estimators. They sort of try to take the output of the frequentist estimator and apply a Bayesian interpretation to it, make horrific mistakes that are mistakes both from the frequentist perspective and from the Bayesian perspective. And you might say, well, you know, why don't you just use Bayesian estimators if you want to use the Bayesian conception of probability? And you get, you know, some mix of answers, you know, a lot of things. But the bottom line is a lot of people don't know how. And, you know, even among those that possibly could learn, worried about, well, you know, people will criticize my results as being subjective if I use the Bayesian estimators, even though they adopted this sort of subjective perspective on probability, that its degree of belief in something is true at the outset. So in terms of what's actually going on in journals and other people who estimate stuff, it's a very weird, contradictory sort of state of things. And with the rstanarm package we're going to talk about today, it basically tries to make it easy for people who are in this sort of weird, contradictory, confusing state of things to estimate models using STAN as the thing that draws from the posterior distribution, and facilitate them doing the analysis that they probably think that they're doing, but they're just sort of so that's where we're headed into today, after we say that because Columbia and all that, Columbia got a bunch of grants to develop STAN, try to use STAN for business purposes, and that creates the appearance of a conflict of interest that you all should be aware of before learning the more stuff today. I also feel that I should disclose the fact that by putting the rstanarm package on CRAN, I'd probably cost myself way more money than Columbia pays me in a year, but okay. So we want to do, before we get into rstanarm necessarily, want to do a comparison of how you would write a function in the STAN language if you were going to analyze the sampling distribution of the ordinary least squares estimator over data sets of size n versus how you would write the logarithm of the posterior kernel if you were going to do this from a Bayesian perspective, and show how in this one case you can make those answers sort of coincide. So over on the left, oops, anyone that does this, in black here, we have a function that's going to return a matrix of the estimated point estimates by ordinary least squares. So that's for the intercept, for the slope, and for the error variance. So it's going to be a matrix with 3 columns that's being returned by this. It's going to take in S, which is the number of simulations I want to do. It's going to take in the true values of the parameters, alpha, beta, and sigma. Remembering everything having to do with frequentist probability is conditional on the parameters, which makes it extraordinarily weird if your sort of goal is to estimate the parameters, and all the probability statements that can be made about it are pre-data and conditional on the parameters. Taking those parameters as given, even though if you're estimating them sort of by definition, you don't have them. But for the purpose of establishing what is the sampling distribution of an estimator over data sets of size n, then we condition on the true values of those parameters, take them in as arguments to the function. Final argument to the function is a vector. You don't have to specify its size, but of size n for my predictor. So this is just going to be analyzing the sampling distribution of ordinary least squares when I have one predictor variable, but it generalizes fairly straightforwardly to the case of multiple x variables that I'm using to predict with. So I initialize a matrix to hold the output. Again, that's going to have 3 columns, one for the estimated intercept, one for the estimated slope, one for the estimated error variance. Get in, which is the number of observations I'm dealing with. I want to make a centered version of my predictor. That just makes things a bit easier from both the frequentist and the Bayesian perspective, but doesn't really affect the slope or the error variance. It just changes the interpretation of the intercept. And then before I get into any sort of loop, I write mu, the conditional mean function, as alpha plus beta times x, so intercept plus slope times the centered predictor. That's going to be a constant throughout all these simulations that I'm doing, as is the sum of squared values of the centered x, which appears in the OLS estimator. So then I fall into my loop over simulations, conditional on my parameters and my x and whatever. I allocate vectors of size n for the outcome and for the residuals. I do an inner loop from 1 to the number of observations, where I compose the nth element of y as the nth element of mu, so the conditional mean, plus a draw from the normal distribution with mean 0 and standard deviation sigma, which constitute the error term. So my outcome, simulated outcome y, consists of part, which is deterministic. It comes from the conditional mean function mu, which is a function of x, namely a linear function of x, and a stochastic part that comes from the error term, which is a normal distribution with mean 0, standard deviation sigma. After I've filled up my simulated outcome variable, I can estimate the intercept as the average of that, given that my predictor has been centered. And then the slope, I just solved the normal equation for a slope, which is the sum of the element-wise product of y in the centered version of x, divided by the sum of squares of x, which is a constant. So that's my estimated slope. Given my estimated intercept and my estimated slope, I can obtain the residuals by subtracting the conditional mean function, but inserting in my estimates for the slope and for the intercept. And then my estimate of the error variance is the sum of squared residuals divided by n minus 2 in this case, because there's two parameters that I'm estimating, the intercept and the slope. So I do that all s times and return the outcome. And that gives me a distribution, particularly in the first couple columns, a distribution of point estimates across data sets of size n that could have been sampled from this population, holding x the same across all those data sets. And you might or should ask yourself the question, how does that make any sense at all in a social science context? How could you do the same research design s times and have the predictor, or really all the predictors, if we're doing this with multiple x variables, be the same across those s data sets? And that is impossible to imagine from a social science perspective. It's a little bit easier to imagine from the perspective that Fisher and those people back in the day were taking on when they tended to think about doing this in the context of experiments, particularly experiments on like plants and agriculture and stuff. And so if you're one of those, researchers, then it kind of makes sense, or it could make sense to say, okay, if we're like in a greenhouse, we could, get data on the output of plants and stuff every year. And if we wanted to, we could give them the same amount of water every time we did the experiment, or the same soil composition, or the same temperature in the greenhouse, or whatever. So as agricultural researchers, it's slightly within the realm of possibility that we could control the values of x. And if we want to fix them to be the same thing every time we do these s experiments, we could do that if we wanted to. Probably didn't happen in reality, but you could sort of imagine it happening. But in the realm of social science, where the researcher has essentially no ability to specify what your x values are, except maybe for one treatment variable that gets randomized, but your age and your income and your race and your gender, all those things, it's not like the researcher assigns those. You just sort of take them as exogenous unknowns. And so the idea that we could do anything in the social science s times and have the same predictors each of those times is just laughable. And so the distribution that we get out from OLS that assumes this doesn't really apply to anything in social science. So the whole idea of ordinary least squares being the best linear unbiased frequentist estimator is for the case where x remains fixed in repeated simulations over S data sets, and the only thing that's changing are the random errors. Now, you can work out the distribution of ordinary least squares across data sets, relaxing the assumption that X is the same all S times. But that's something that isn't really done except maybe in like PhD level courses in economics, as far as the social science goes, actually working out that distribution. And the reason for that is ostensibly, well, it's like a lot of work to go through, and it's not that different from what the distribution of the OLS estimator is in the case where X is fixed across data sets. However, in the case where X is not fixed across data sets, we can't work out what the distribution of the estimator is for a finite number of observations. So that's one thing. And moreover, it's not unbiased anymore. It's only an unbiased estimator when X is fixed. So as N gets large, it gets closer and closer, but it's unbiased, or it's biased still for any N. And so if you think about it that way, there's not as much to recommend the ordinary least squares estimator in terms of applying it to problems in the social sciences. Now on the right, in blue here, we have a stand function that looks somewhat similar, but is actually used in a completely different way. This is the logarithm of the posterior numerator of the posterior kernel that you would use if you wanted to estimate the posterior distribution of the parameters. So this is going to be a function of alpha and beta, and it's going to condition on a particular value of y and x. Again, the frequentist thing, it does not condition on y. It evaluates the distribution over all possible ways that y could be constructed through this error term. So all of its probability statements are pre-data and conditional on the parameters. Whereas Bayesian posterior estimation, it's conditional on the data, conditional on the y. You're not talking about any hypothetical data sets that could have happened but didn't. You're only conditioning on the data that you actually have, and in general, you would have priors that would allow you to introduce information about the unknown parameters that is not reflected or fully reflected in the finite data that you have collected. But all Bayesian, posterior distributions are correct given the finite and observations that you're conditioning on. So this kernel function is going to return a single real number, so just one number. We again get the number of data points of x. Again, we center x because it reduces the dependence. And we can construct mu as alpha plus beta times the centered version of x. But there's no loop over s here. This is just, you put in y and x and get out one number. We do construct sigma, which is 1 over the square root of what I'm calling tau here. Tau was used in the Lancaster reading a couple of weeks ago. Before stand, it kind of made some sense to parameterize the normal distribution in terms of the precision, which is the reciprocal of the variance. But that's only for like good samplers. For stand, it doesn't really make sense. And insofar as people have any intuition about these parameters, it's more likely to be about the standard deviation than about the variance, much less the reciprocal of the variance, which is the precision tau. Nevertheless, in order to make a point that I want to make in a second, it's necessary to parameterize this kernel function in terms of tau, the precision, and take sigma to be an intermediate quantity that's just 1 over the square root of tau. So in this, tau is the exogenous unknown, and sigma is the endogenous unknown. I would know it if I knew tau, but it's just an intermediate quantity along the way. The reason to parameterize this in terms of tau is that you can use a Jeffreys prior on the precision tau. Remember Jeffrey's prior for a positive scalar random variable is 1 over its reciprocal. So the logarithm of that is our negative logarithm of tau. And then we add to it the value of normal underscore LPDF, which is a function of mu and sigma evaluated at the particular y that we have. Now this normal LPDF, all the functions in STAN that end in LPDF or LPMF are going to return scalars. That's a bit different from their behavior in R with like dnorm and whatnot. So if you give normal LPDF, vectors, it's going to add the logarithm across all n components of those vectors and return out a scalar instead of returning n values. It's only going to return the sum log PDF of all that. So negative log tau is a scalar, normal LPDF, whatever, is also going to be a scalar, and that's what gets returned. So the negative log tau is the Jeffrey's prior on tau, normal LPDF is the log likelihood of the parameters, and in this case, for the purposes of illustration, I'm implicitly using improper priors on the intercept alpha and the slope beta. Now, why might I do that after we spent, I don't know how much time saying that that would be a bad idea a couple of weeks ago? The reason why I'm doing it in this case is with this choice of improper priors, the posterior distribution can be worked out analytically. We wouldn't actually need Hamiltonian Monte Carlo to draw from this posterior distribution. This is one of the few cases where we can get like a non-trivial posterior distribution analytically. And that posterior distribution conditional on y and x, whatever, is going to be multivariate t distribution. So the margins are distributed student t, and the center of that t distribution is going to be the OLS estimates. And like the standard deviation of that posterior distribution is going to be the standard error of the OLS estimate. So if you took like one of these y's that we create with the frequentist perspective of doing things, conditioned on that and got the posterior distribution, you wouldn't need to do MCMC. You could just do ordinary least squares and use the OLS estimates to say what the posterior distribution would be, because it's going to be t distribution with centered at the OLS estimates. And so the OLS estimator and the Bayesian estimator are always conceptually different things. But in this case, the estimated sampling distribution of a point estimator across data sets happens to be the same distribution as the posterior distribution of the parameters for this one data set that you have. They're both student t, but they're conceptually different things. One pertains to the distribution of the estimator across data sets, the so-called sampling distribution. The other is your beliefs about alpha and beta and sigma and whatnot, conditional on the data that you have and the priors that you started out with. So although it's the same distribution, it has a different interpretation. So that's why I refer to this particular example as a total eclipse of the posterior, because the frequentist sampling distribution and the Bayesian posterior distribution exactly align with each other, but they're different things in the sense that the sun and the moon are different things. But once every, I don't know, however many years, they line up, and birds and squirrels and whatever freak out and all those sorts of things. But it doesn't mean that they have the same interpretation. And a fundamental aspect of this sort of weird state of affairs that I alluded to at the beginning, where everyone accepts the Bayesian conception of probability, but almost all of those people only use frequentist estimators, is that this sort of alignment happens routinely when there's really only one case, this one, in which it does. And that they think they have sort of license, or really they don't know what they're doing, but they act as if they have license to take this frequentist estimation stuff, and it implies some Bayesian posterior thing that they can then use to make probabilistic statements about the unknown parameters in their model, which if they had any sense of history, they might immediately be suspicious, because Fisher created maximum likelihood estimation and a bunch of other things in order to destroy Bayesianism before it could take firm root in science, particularly the part of science that Fisher was interested in, is evolutionary biology, but he was interested in sort of pushing his view on methodology, across different sciences. Insofar as Fisher had sort of any inclination to the social science, even though social sciences weren't even a thing in the 1920s, but insofar as his research had any implications about people, it was to try to sustain his views, which were pro-eugenics. So, science has moved away from that as far as it can go, but somehow kept the frequentist methodology for, estimating these things, which is, another very odd historical oddity. And moreover, okay, so in this one case, we could take OLS estimates, and that implies us the posterior distribution that goes with the kernel on the right. But does that make any sense? Well, we've already said you have to have improper priors on the intercept and the slope in order for this to line up. So that's not even a probability distribution. That sort of entails that you think every real number is equally possible for the intercept and the slope, when everyone would probably say the values that are closer to 0 are much more likely than things that are like a zillion, or some number that's like a zillion squared, or any other real number that you're ostensibly saying is as equally likely for the parameters as anything else. Also, you have to put a Jeffreys prior on tau, whereas that's another improper prior that is necessary in order to get this kind of alignment. And no one really says that Jeffreys prior on a precision makes any sense. We sort of said there might be some situations in which Jeffreys prior on a scale parameter makes sense. So Jeffreys prior on sigma could be kind of a reasonable thing to do. But Jeffreys prior on a precision, in addition to being improper, it has a mode of 0. So you're saying the most likely value for tau is 0. And if tau is the reciprocal of the variance, you're saying the most likely value for the error variance is infinity. And if you actually thought that, then why would you be collecting data? But you don't think that, because it doesn't make any sense. And so for a lot of reasons, this posterior distribution is suspect, but it is the posterior distribution that would be implied by OLS estimates. So in basically the bottom line of this, in order to use ordinary least squares and give it a Bayesian interpretation and treat the confidence intervals as credible intervals and all kinds of things like that, you have to have these weird priors. And it only works in this case. In general, you can't just take frequentist estimators and give a Bayesian interpretation to them. If so, why would Fisher have created them? So that's a bit on that. Any questions about comparison of these two things? Again, they're both on Canvas. Or I didn't actually say that before, but they are on Canvas. Questions about any of the syntax? So for the next month or so, the course actually gets a little bit easier, or at least harder at a slower rate, or more like other courses in that the main thing that you have to figure out is like how to put in the R syntax to get out what you want. But we want to use this sort of lull, for lack of a better word, to keep reinforcing the stuff that we learned over the first month or 6 weeks in terms of thinking about things probabilistically, writing them in the Stan language, the Bayesian interpretation of things, etc. And so when we get back from spring break and the difficulty starts to accelerate a little bit again, we're in better position to be able to handle that than we otherwise would. Questions about any of this? Okay. So you can expose that, you can create yourself a data, you can create true parameters, which in this case is an intercept of 0, a slope of 0.5, and an error standard deviation of 10. You can draw 10,000 times in the distribution of the OLS estimator and take the average over those 10,000 data sets that you simulated, and you find that the average of the estimates is extraordinarily close indeed within numerical error or simulation error of the true values. So if we fix x to be, whatever, the log factorial of the first 16, 17 integers, the ordinary least squares estimator is unbiased, which is to say the expectation of the estimator is equal to the thing that it is estimating. Another weird historical thing is like back in Fisher's time, they sort of knew that they'd found like 5 frequentist estimators that were unbiased, and they just assumed like by next year somebody else would have found like another 20, but they never did. So we're still stuck with the same 5 estimators that are unbiased that have, pretty much always been the case. Ordinary least squares being one of them. We can work out the sampling distribution for a finite n. But in most other situations in which a frequent estimator has been proposed, 1, we only know its distribution across data sets that are infinite in size, and 2, for any finite n, we know that they're biased. So there's sort of what sounds good about ordinary least squares in terms of being best linear unbiased frequentist estimator doesn't hold for frequentist estimators in general, and isn't all that it's cracked up to be anyway. But what we can do is calculate the so-called true standard error using the true sigma and the true sum of squared x's, which again, it's staying fixed for all s of our data sets. So that's known as the true standard error. And if we divide the difference between the estimated slope minus the true slope and divide that quantity by the true standard error, the distribution of that statistic, known as a test statistic, is exactly standard normal. So in black, I put up the simulated line. In red, I put up the sort of analytical line based on the normal CDF. This is a CDF plot. And you can't even tell the difference between the 2 lines because there is no difference. Across data sets, if you subtract the estimated OLS, if you subtract the true slope from the estimated slope and divide by the true standard error, so the only thing that's changing is the estimated slope, the distribution of that function, test statistic, is exactly standard normal. And if we knew the true standard error and the hypothesized value of beta, we could, figure out what is the probability of getting an OLS estimate that is greater than 2 standard errors or whatever from the null hypothesis. And that's the sort of thing that's done with a lot of frequentist estimators under the assumption that n is large, and thus the fact that you estimate the standard error doesn't induce a lot of damage. But this is based on the true standard error. But if you don't have the true standard error, what can you do? Well, you could obtain the so-called estimated standard error of the estimator, which is taking the estimated variance, so the third column being returned by our simulations here, take the estimated variance, divide by the sum of squared x's, take the square root of all that. So that is what we estimate the true standard error to be. And if we divide the estimated slope minus the true value of the slope by the estimated standard error, then the distribution of that statistic is no longer standard normal. It's now student t with n minus k degrees of freedom. K is 2 in this case because we estimated an intercept and a slope. And again, you can see the sort of simulated line in black, the true line based on the CDF of the student t distribution in red, and there's no real difference between those lines. I also put up in green the curve for the standard normal, and you can see that that green curve is actually slightly different from the other two curves, especially around here and around here. So you might have thought that my plot gain was just like a little bit off, but they actually are like that much different when you have 15 degrees of freedom. So you can get a bigger difference between a student t distribution and a normal distribution with smaller degrees of freedom, but the student t distribution rapidly converges to the standard normal as the number of degrees of freedom gets even moderately sized, like 15 in this case. So basically there's very little difference between student t and standard normal, except in the case where you have very few observations or you're estimating a ton of parameters. And so when you see the t statistic that comes out in R, whatever you might use, that is evaluating this function under the null hypothesis that the slope is 0. And we know across data sets that function is going to have this t distribution. And so we can calculate a p-value, the proportion of times, proportion of data sets that someone would get a more extreme estimate of the slope than the slope that you got, conditional on the fact that the true slope is 0. So just again, the p-value, if you interpret it correctly, is the proportion of times somebody else with another data set of size n that was sampled from the same population as you that happens to have the same x's as in the data set that you have, the probability that other person overestimates the slope more than you do, conditional on the true slope being 0, whatever that probability is, that's a p-value. And when you say it like that, it becomes more clear why eventually, after like decades, the Journal of the American Statistical Association would say, you should not be using a p-value for anything. It's a conditional probability, but it's not the conditional probability you want. It's not like the conditional probability that a hypothesis is true given the data. It's a conditional probability that somebody else with a different sample from the same population as you gets a more extreme estimate of the slope, given that the slope is 0. The probability that someone overestimates the slope more than you do, given that the slope is 0. And for weird historical convention reasons, if that was less than 0.05, then people believed your point estimate. But it doesn't follow at all from the definition of a p-value. And what people do with these p-values today is kind of a amalgamation of what Fisher and Neyman and Pearson, there are different perspectives on how to do frequentist estimation. They were in conflict with each other. So there's a lot of weird historical oddities that the Journal of the American Statistical Association was trying to belatedly address a couple of years ago when they said don't use p-values. But it was like many decades too late. We have all kinds of papers published in different journals that, on the basis of their p-value being 0.04 or whatever, that has like no particular difference from a p-value being 0.06, because the concept of a p-value is not that important for making scientific conclusions, in particular, whether or not it's less than or slightly greater than 0.05, makes no scientific difference at all. And yet, some papers were accepted because it was, 0.04, and others were rejected because it was 0.06. And so we have, entire subfields where we don't know if like any of the published articles in the journals are any better than all of the articles that weren't published because their p-values weren't quite low enough on this ridiculous criterion from a scientific perspective for judging the worth of papers. But that can be done, and moreover, it's objective. It doesn't depend on anyone's beliefs about anything. This is like a true distribution across data sets. So it's useless, but it doesn't rely on anyone's beliefs, unlike a posterior distribution, which is going to be a function of the prior. The other important part about frequentist analysis is the power of the test. Let's say the beta is 0 against a one-sided alternative. So with these 17 observations on X, if we take our distribution of point estimated slopes, 10,000 of those, subtract the hypothesized value, which is 0, divided by the estimated standard error, the proportion of times that is greater than the so-called critical value from a t distribution with 15 degrees of freedom is like 0.624. So we do interpret that as saying for these particular 17 values of X, which are unlikely to be the same values of X in anybody else's replication of this, our expectation over the outcome variable before we see the outcome variable, we would expect to reject a false null hypothesis that beta is 0 in favor of the alternative hypothesis that beta is positive at the 5% level with probability 0.624 when the true value of beta is actually 1/2. So when doing simulations, you can calculate these things. Occasionally you can calculate them analytically, but what good does this really have, or what use does this have in practice when we don't know the true value of beta? And so this probability statement that is conditional on the true value of beta isn't really that something that we can grasp. What a lot of people do is first estimate the slope or whatever, and then come up with the so-called estimated power, which is not a pre-data statement, and hence makes no sense, and is extremely misleading. So always keep in mind these frequentist probability statements about estimators are before you see the data, and they're integrating across data sets of size n. Whereas the Bayesian posterior thing is just conditional on the data you have, your beliefs about the parameters that generated the data that you observe under the model that you are specifying. And there's no asymptotics, and there's no what's the distribution of this across data sets, any of that. And things have a relatively straightforward interpretation in terms of Bayesian probability. So let's do one of those. But in doing that, we need to come up with a generative model, a model we can simulate from. And so this is going to be a model to explain the variation in prices of diamonds. So let's write this out here in terms of exogenous, endogenous, known, unknowable. Okay, so I'll get you started by saying the endogenous known is going to be the price of the diamond. So that's what our model is attempting to explain, what we're modeling. That's our outcome variable. Now, what would go in the other boxes for a model like this? Who knows about diamonds? No one knows about diamonds. If you don't know about diamonds, raise your right hand. Okay, possible. Yes, diamond expert.
Whoa, easy. I want one.
Okay, that's like an infinite times more than I have, so.
So I mean, size matters.
Good.
Color matters.
Okay, wait, no, not so fast. All right, so I'm gonna spell you the N as well. We know how many observations that we have. We have sort of size on all three dimensions. So this Y is not the outcome Y, but it's the length or the width or the height, whatever we want to assign.
The weight, right?
Yeah. Oh, the weight. Okay. Good to know. What else you
Color
got?
matters.
Color. Yeah, the black diamonds are cool. I know that.
Well, well, sure.
Wait, that's not a thing?
I mean, maybe they are. I mean, I think skiing.
Okay.
But I mean, you want your diamond to be clear, right? Which is,
Clarity.
I think, yeah. You don't want the impurities in them. The
Impurities.
it's clarity.
Wait, the impurities
I
are the
think the
clarity?
color is like non-yellowy, right? And then clarity is like lack of impurities. I might be wrong about this. Like I said, about one diamond.
You have an alternate diamond expert? You don't know.
Maybe it depends on the season, like maybe they.
Season. Yeah, like Christmas, they have a lot of commercials and stuff about that. Yeah.
Carrots.
Oh,
I don't know
carrots.
what those.
That's weight.
Oh, wait. Carrots are the same as weight?
I'm pretty sure.
Okay. Or
And
question
usually the
mark
X, Y,
there.
Z, like, yeah, it's okay.
Oh, wait, another statement? Oh.
And the cut, how you cut it.
Oh, the cut. Right, okay. Now we're getting somewhere.
Also,
I-
and maybe whether they were harvested like ethically. or not.
Yeah, so blood, diamonds. All right. Anything else that would go into our exogenous knowns for a model of diamond prices?
With brand come?
Hmm?
Brand?
Oh, the brand. Okay. Should have made a bigger box. All right.
Origin.
Origin.
Oh, so yeah. I sort of had that as blood diamond. Other things? Okay, so what would be the exogenous unknowables? And we could have data on the purchase of diamond, in which case that would be a different outcome variable. But these are, I guess, just going to be like data at the wholesale level, maybe. But anyway, so like, what would be the exogenous unknowns in a model like this? Like a linear model like this? Like in some way, shape, or form pertaining to the thing that we just got through talking about. Yes. So like the coefficients on all of these things. So we got like alpha and we got beta 1 and we got beta k. Right? But if we're going to have, you know, all those parameters, then we're also going to have priors on those. And again, we don't have to know the correct values of the parameters. We do have to know what we believe and that what our beliefs are going to be reflected in more things that are exogenous knowns and being passed in. So what would go in endogenous and unknowable? Now, what implications might we be able to draw from this model if we knew the values of the parameters?
The predicted price of the diamond.
Right, so we could predict the price of a future diamond. We could answer questions like, would it be a good decision to buy a diamond? Like maybe some things like, I don't know if this model exactly, but maybe with a somewhat different model, like what would be the implications if we were to regulate the diamond trade more or differently, something like that. Those are all questions that we could answer if we knew the parameters in a model like this. So fortunately, there is a data set that comes in the ggplot2 package called diamonds, which have these variables that are a reasonable subset of the predictor variables that we sort of collectively arrive at in terms of the cut and the color and the clarity and the size of it in terms of width and height and depth, those sorts of things. It doesn't have where it originated from or like who is the retailer or anything like that. But we have a bunch of variables here. And we might say, okay, now we have to come up with priors on these sorts of parameters. First, we have to ask ourselves, would it make sense to have a linear model for price as a function of these things?
I will say no.
No.
So larger diamonds are rarer, and they exponentially increase in price.
Right. So we probably have like a skewed distribution of the outcome, even conditional on the predictors, etc.
There's also step functions as well. There's certain thresholds on size
sorts of things. Yeah. So given that we're going to have to estimate a linear model, what might we be able to do to make a linear model for this more reasonable in the presence of an outcome that is positive and highly skewed?
Okay. Log.
Log of the outcome?
Yeah.
Right. So that if we log both sides, that would turn a multiplicative model into a model that is linear in the logarithms of size and, you know, so log price is a function of log size and other stuff like that. Okay, so that might help. But even in logarithms, you know, is it the case that these things are going to have a linear relationship, or we, you know, anticipate there being linear relationships? Probably not. Maybe. But there's no great reason to believe so going in. And so one of the things that we could do, a couple of things we could do would be to include interaction terms or polynomial terms to, you know, get at some of this higher order increases, etc. But that is going to be a lot of coefficients. And it's going to be kind of hard to specify a prior over all those things. Expressing our beliefs is like, what is the interaction between like y and caret, and how that affects the log price. It's going to be a hard sort of task to think about, although in principle it could be done, and with enough observations it wouldn't matter so much what your priors were. And in this case we have almost 54,000 of them. However, I've made this easier on you in the function that we're going to talk about on the next slide. The only thing that you have to specify in terms of prior information is a prior mode of the R squared for a model that is linear in logarithms for something like this. So what would you guess is your prior mode for this linear in logarithms model we're going to estimate? How much of the variation in price do you think could be explained, or log price could be explained in by these variables here? Not so much diamond experts, are you?
Your next slide says
0.8.
Your next slide says
Oh, my next slide says 0.8. Well, that's just what I thought. I clearly don't know what I'm talking about. What do you think? Even though we're going to do 0.8 going forward.
I mean, they're commodity goods, and products can get much better than 0.8. Given that these are pretty much the dimensions that we walk into a diamond store, they sell you on, and they're the ones that they're certified with.
Yeah. So in a situation in which there's kind of like a formula that maybe the diamond people are using, but you don't know what it is. But if like all the diamond people are kind of using the same formula, then you might anticipate the R squared being, a lot higher than it would typically is in like psychology. Research. Yeah, that would make sense. In general, with like market competition, there's probably some pressure to for different sellers, even if they're not like colluding with each other, to behave similarly. They have similar suppliers in, places that have diamonds and whatnot. So we're going to do 0.8. That kind of seems reasonable to me. It should probably seem reasonable to you. Definitely on the high side compared to probably most things that we would be modeling in the social sciences. So how do we do that? We call the stan_lm function in the rstanarm package. Before doing this, you're going to want to tell R to use all its cores because we can estimate multiple Markov chains simultaneously. Indeed, by default, it's going to be 4. So the syntax for stan_lm is the same as lm, except you put a stan underscore out front of it. So we have a formula, log price, depends on the interaction between caret and the size variables. And then we have factors for the quality of the cut, the color or discoloration, the clarity, etc. You specify what data set all of these variables from. And then the only difference between stan lm and lm is that you also have to specify your prior beliefs about the R squared parameter, which we just got through saying. In this example, it's going to be 0.8. And that's my prior mode from which stan lm can figure out the rest of the prior stuff for you. Indeed, this is the maximum entropy prior on the coefficients for an expected log R squared. Nobody really has any intuition as to what a log R squared is. So just sort of put in your prior mode about the R squared, and then that's fine. You can go from there. I'm going to subset this. There's a few cases where they have like negative values for the Z dimension. That makes no sense. So we'll just discard those observations rather than taking the logarithm. And what we get back is draws from the posterior distribution provided by Stan using Hamiltonian Monte Carlo. And this is basically a list of a bunch of stuff, but it can be coerced into a data frame or a matrix or other things. And it's basically just a 4,000 draws by 28 columns because there ended up being 28 parameters, or 27 actually, in this model. So I'm getting a posterior distribution in a 27-dimensional space. And I get like 4,000 draws from it, 1,000 each after warm-up from each of 4 chains, which is what the defaults are. And when I coerce this into a data frame, you can see the first few values of the draws on the coefficients and intercept of all of these variables. So we're going to show some like summary output of these things, but always keep in mind that that output is already derived from the raw draws from this posterior distribution. And you can get the raw draws yourself and do anything you want with them. But if you just like print the output, you get something like this, although by default it only has 1 decimal place, which is usually all we can estimate with any accuracy at all. We have so many observations, and this is such a predictable thing that we actually could get some precision in the 3rd or 4th decimal place here, but I'm just showing you so you know how to do it. The main 2 columns in the output are the posterior medians. So it's fair to say conditional on these data, no other data, but these data and your priors that you came into it with. There's like a 50% chance that the intercept is less than 0.7662 and a 50% chance that it is greater than 0.7662. And the same for all of these slopes on those variables and whatnot. The second column says MAD_SD. That stands for median absolute deviation. So the median of the absolute differences from the median. And then it's squared up by some, scaled up by some number 1.4 or something. So that is the estimator of the posterior standard deviation, assuming the posterior standard deviation to be normal. Anyway, this median absolute deviation is a measure of scatter for the margins of the posterior distribution that is robust to outliers. So there's some chance that the tails of the posterior distribution might be screwed up or something like that, in which case you don't want to be using an estimator that is overly influenced by maybe some of these things that aren't quite right. So we use a more robust estimator to get the estimated standard deviation of these posterior distributions. But basically what we're saying here is posterior median, posterior standard deviation for each of these 28 margins that we got the posterior distribution of, and these are directly calculated from the 4,000 draws that I was referring to on the previous slide. And so if you just sort of imagine this as like point estimate and this is standard error, this looks a lot like what people who use frequentist estimators are looking at when they see the output of their thing with like LM. But this is actually based on a posterior distribution, with the prior that we specified in terms of the prior mode on the R². And this is the posterior distribution that comes out. And we can make probabilistic statements about parameters from Bayesian perspective that you can't from a frequentist perspective, like saying there's a 50% chance it's less than the median and 50% chance that it's greater than the median. And here's what the posterior median is, as opposed to like, here's some point estimate that has no valid probabilistic interpretation. So that's the basic output you get out of something produced by StanLM. If you do summary, you can get a more detailed output. It also shows you some stuff about what model that you estimated. This cuts off, but if you go to the bottom, it also shows the effective sample sizes and some other diagnostics, which turn out to be fine in this case and almost always are when using rstanarm, but it's something to be aware of. It can go wrong depending on your data. If your data are not that very amenable to a model that you're estimating, then yeah, things can get screwed up. We can estimate the ratio of the effective sample size to the nominal sample size, which was 4,000, using the NF ratio in the Bayes plot package, which comes with rstanarm. We'll talk about it more as the weeks go on. And this is really illustrating of how great an algorithm no U-turn sampling is. So we estimated a somewhat complicated linear model, had all these interaction terms, had 27 coefficients and intercept that we were estimating, and the ratio of the effective sample size to the nominal sample size is at worst 0.54. So more than 2,000 on a nominal sample size of 4,000. But that's just a worst case scenario for like the intercept and for sigma. For most of these coefficients on these variables here, it's near or even above the nominal sample size. And that's because there's a tendency for nuts to go far away from the previous iteration. And so the first order autocorrelation is negative. Hence, the effective sample can be 25, 33% greater than the nominal sample size. And it is for these cut dummy variables that we estimate the intercept of. You could not get that with Metropolis, Hastings, Gibbs, anything else. That sort of super efficient performance basically only coming from no U-turn sampling. And that's why we can get away with only doing like 4,000 draws from this posterior distribution, whereas if you're doing with this Gibbs and whatever, you do millions because your effective sample size goes to like 0.0001 or something like that. So you need to do a million nominal draws in order to get like enough effective samples to estimate this thing reliably, whereas with Stan, we can do it with much lower number of nominal iterations. Credible intervals, so these can be obtained by calling posterior underscore interval, and you can specify whatever probability you want. This is another thing that we can make probabilistic statements about. This is what most people who use frequentist estimators think confidence intervals are, but they think wrong. And if they're going to think that, they should use the estimator that corresponds to what they think, which would be the Bayesian one. So, with each of these two numbers, we can say there's an 80% chance under the posterior distribution that the parameter is between this and that. And there's like a 10% chance that it's less than the smaller one, and a 10% chance that it's bigger than the big one. And so, here we're basically saying there's a, this is only the 2 digits or whatever, but the posterior R squared is actually, there's an 80% chance it's between 0.98 and 0.98. You have to go into like the 5th decimal places to start to see the difference. So this is actually even more predictable process than what we thought in our prior of 0.8. It updated our beliefs about the R squared to something that is even closer to 1. But perhaps more importantly, we get very precise credible intervals. These are what they're called because they're not confidence intervals on like how much more does the log price expect to differ if it's premium versus relative to the baseline category, which is like whatever is worse than good. Again, very precise. There's an 80% chance it's between 0.13 and 0.14. So we can make these probabilistic statements about the parameters. Last thing for today, how will we come up with some way to say, well, what would be the effect if we were to increase the carats of the diamonds by a small amount? How would you get that based on the model, the posterior distribution we've obtained? Don't everybody answer at once. It's not totally easy. One, because we're dealing with the logarithm of price, but when we want to make like conclusions, we would want to put it in like actual price. Also, we've got all these interaction terms between carat and the size. So this one is just for one that has like size of 1 on X, Y, and Z, so the logarithm of it is 0. For other sizes, it's like harder to work out what the effect, but even still, it would only be an effect on log price. And the answer to this question and all sorts of questions like that is you don't interpret the coefficients of the posterior distribution. You interpret what the model predicts under different counterfactuals. So there's a disease that comes from like the frequentist approach that you can only look at the parameters because that's kind of all you get. But with the Bayesian approach, you get a whole posterior distribution, and it's from a generative model. So you can push your posterior distribution through your model to see what you would predict, and you can see how your predictions change if you were to change caret from whatever it is now to like 0.02 more. I think this is actually in grams, and 0.02 of a caret, of a 200 milligrams is a caret. So this is sort of increasing it by 1 caret. And we can plot a PDF or a CDF of whatever we want in terms of the regular units. So I can get my predictions on the log scale of log price, EXP those up to get predictions in regular prices. And now I can plot, whatever I want, such as, the ratio after I increase the number of carets minus the original thing divided by the original to get sort of how much does it increase in relative terms. And that's the CDF. So we'll do this a lot more on Thursday and other days as we go along. But basically only in the very simple case where you have a linear model, no interaction terms, anything like that, can you interpret the coefficients in a straightforward fashion. But you don't have to interpret the coefficients in a straightforward fashion. You can interpret the predictions of the model in a straightforward fashion with counterfactual manipulations of the predictors, and you can explain and present the results of those hypothetical changes in the, in terms of observables, in the original units. Even if you estimated the model with like logarithms and interaction terms and stuff like that, we can get very simple plots of the predictions to explain what our model implies. And that's what we want to be doing when we actually have a posterior distribution that we can push through a generative model. So do the other chapters of reading from the Gilman and Hill and Vitari book. If you didn't pick up a reading on last week, I have some more of them here. We'll talk about generalized linear models on Thursday, again, using the rstanarm package and stan GLM rather than stan LM. So I'll see you then.